Hello again. In this video we're going to look at several theorems whose eigenvalues are distinct and independent. In our last example of our last video, the eigenvalues of that matrix were distinct. They were different. What are some theorems that go along with that? Let's start with the first theorem here. Theorem 2. Theorem 2 is from our first section of this chapter. And it says, if you have a set of eigenvectors that correspond to a distinct eigenvalues, lambda 1 through lambda r, of an n by n matrix, A, then that set is linearly independent. The actual proof of this theorem you can look at is on page 272. And what they do is they do a contradiction. They say that, okay, let's assume that it's not dependent, and then you're going to see that that's not going to work. It's going to be, they're going to be independent. But you can check that out on your own if you want. The one that I want to concentrate on is Theorem 5 from this section. So we know that we can diagonalize an n by n matrix if and only if A has n linearly independent eigenvectors. We actually used this theorem in the last section, but now let's go ahead and look at the proof. So I'm going to start with, let A be an n by n matrix this way with n linearly independent vectors. So I'm going to prove this way. And I want to show that A is diagonalizable. So I'm going to let V1, V2, Vn, since we have n independent eigenvectors corresponding to, let's call them lambda 1, lambda 2 to lambda n, respectively, where P is the matrix of all those eigenvectors, and D is the diagonal matrix with the lambdas in the order of the eigenvectors, which is what we did with this theorem last time, because they did say that right here that this is what it means for it to be diagonalized. And D is a diagonal matrix. P is n linear independent eigenvectors of A, where the diagonal entries are the eigenvalues of A corresponding respectively to the eigenvectors of P. So I'm just going to look at A times P. So here's A and here's P. So I'm going to bring that A in, and then I'm going to look at P times D. So here's P and here's D. Multiply that out, we're just going to get lambda 1, because it's a diagonal matrix. In the first entry, right, this is a 1 by n, and n by n. So you end up with a 1 by n. And the second row, second column is just going to be lambda 2, b2, and so forth. And because each of these are eigenvectors, we know that A sub vi is equal to lambda I vi for each I, 1 through n. So therefore AP is equal to PD. And since V1 and V2 were independent, let's make this a little smaller so we can see that. If you remember, I assumed that they were independent. We know the columns of P are therefore independent. And by the invertible matrix theorem, we know that P is invertible. Therefore, we can multiply both sides by P inverse of this equation, and we have that A, you can diagonalize A. Let's make this smaller so you can see the whole thing. That's real small. We can also go the other way around. We can show that if you can diagonalize A, then A has n linearly independent vectors. The proof of that is in the book on page 284. So let's go ahead and look at the next theorem. So we know that an n by n matrix with n distinct eigenvalues is diagonalizable. And this just comes from the following two theorems above. So again, if we have an n by n matrix with n distinct eigenvalues. So if we go back and look at the first theorem, we know that tells us we have n distinct eigenvalues, that those n distinct eigenvalues are linearly independent. If they're linearly independent, we just showed that you can diagonalize A. That's exactly what this says. If you have n distinct eigenvalues, then you can diagonalize A. And that's what it says here in the little proof. So when you have a distinct set of eigenvalues, everything is good. You know it's linearly independent, you have n of them, and you know that you can diagonalize it. But what if it's not distinct? Does it mean that you can not diagonalize your matrix? Well, the answer is sometimes yes and sometimes no. You don't have as many theorems. It's not as strong. So let's go ahead and look at example 3. Example 3 is going to have some non-distinct eigenvalues. So we're going to find them. So we're first going to diagonalize the matrix if possible. So that is, we're going to find an invertible matrix P. This is a definition of it being diagonalized. And a diagonal matrix D such that A equals P, D, P inverse. So how do you find the eigenvalues? Well, we're going to look at the characteristic equation. So here's the characteristic equation. That's the determinant of A minus lambda I. Here's A minus lambda I. Again, all we do is put a minus lambda in for the diagonals. We leave everything else alone. We're going to find the determinant of that. Not as easy as our last example. We don't have any zeros here. So I'm just going to use my first column. 1 minus lambda, a negative 3, and a 3. And the determinants that arise from eliminating the row and the column from that entry. Then I'm going to define the determinant of each. It's a big nightmare. Expand it. I FOILed this out. Distributive property of each of these. Combine like terms inside the parentheses. FOILed out even farther. And I realized these went, actually, before I FOILed out, these went away. So I end up with a nice matrix where I had 2 eigenvalues. Oh, there's a little mistake there. Lambda equals 1 and lambda equals negative 2. Lambda equals negative 2 has multiplicity of 2, so we know that they're not distinct. So is it going to work? Let's see if we can find 3 linearly independent eigenvectors. And we can try doing that by finding a basis for the eigenspace and seeing what happens. So I'm going to let lambda 1 equal 1, since that was one of the solutions. And I'm just going to put a 1 here and get this matrix. And I'm going to solve this non-trivial solution by row reducing it to reduced echelon form to make this a little easier. And I get that x1 equals x3, x2 equals negative x3. So I can put it right into this matrix. And I'm going to let v1, so my first independent matrix is going to be, I'm just going to let x3 be 1. Would be that. So now I'm going to do the same thing when lambda is negative 2. So when you plug in a negative 2 into the same matrix as above, you get a row of all 3's or negative 3's. You get 2 values that are free, and x1 would be negative x2 minus x3, so x would be split up into 2 matrices. So we would have, splitting this up, we'd have 2 vectors. I'm going to call this v2 and this v3. I have 3 independent vectors, so I am okay. So now we can construct a P, because we know P is just, if you remember, the v's. So we're going to be whatever v1 was. There it is. 1, negative 1, 1. v2 is negative 1, 1, and 0 right here. And v3, negative 1, 0, and 1. If you make it smaller, you can see all three. Here's v1, v2, and v3. That is the p. These are very independent. There's no way you're going to get a multiple of this to get either one of these, but you could check it, and therefore there will be a p inverse. So all will be well. And if you remember our d, you have to be careful. It has to be correspond with these. These are all 0. So that should be the lambda 1. So that was the 1. Lambda 2, both of these are negative 2 because they're a double root. It's always a good idea to check it. So you can check this, but it's equivalent to check this because if you remember, we showed you this before, but A, P, D, P inverse, oh, I don't know what that is. If you multiply both sides by P on the right, you're going to get AP equals PD. The only reason you have to be careful, if P is not invertible, then you might not be able to do this, but it has a P inverse there, and we know it's independent, so we know that it's invertible. So if I look at AP, there's my original A times the P, that's right there. You get this matrix. And then if you take P times the D, you get the same thing. So it does indeed work. But it doesn't always work. So example 4 is one that it doesn't work. It has, by the way, the same characteristic equation if you do it out, and we'll do that in a second. So the characteristic equation of A turns out to be exactly the same in the last example, example 3. And so you still get that double multiplicity of negative 2, multiplicity of 2. And however, when you do the one for negative 2, you only get one eigenvector, so you don't get 3. So therefore, you cannot diagonalize it. The P is only going to be V1 and V2, and you need to have V1, V2, V3. So there's no other eigenvalues for every eigenvector A. A is a multiple of either V1 or V2, so it's impossible to construct a basis for R3 using the eigenvectors of A. So by the theorem, it is not diagonalizable. And if you remember, theorem 5 said exactly that. If you had n linearly independent eigenvectors, if and only if A is diagonalizable. I would like to spend a few moments looking at this bit. We've already seen when it's distinct. But let's just check this out. What happens when lambda equals negative 2? So if I look at the A minus lambda I, here's the A, whoops, there it is. And if I plug in a negative 2 here, I should get this matrix. And now looking at the homogeneous solution, if I row reduce it, this is what I get. I interchanged 1 and 3, divided everything by 3, got 0 for here, which really end up zeros in both. 4 times the first row, added the second row, and then the same thing here. Then I got a 0 there. So I end up with x3 equals 0. So I just have x1 plus x2 equals 0, because I really have x1 plus x2 plus x3 equals 0, but x3 is 0. So if I write that up, the only thing we have free is x2. We know that x1 equals negative x2. You can see we only have one vector. We have that v2 there.